Good morning, Professor.
Good morning. Good morning. right, well, let's go ahead and get started. Anyway, um, well, shoot. All right, well, it's working. Let's go. Today we're going to do chapter 9. Chapter 9, shoot. Chapter 9 is the ideal gas laws. Tomorrow's election day, please vote. And in chapter 9, we are going to start off by reviewing once again the kinetic molecular theory, pressure volume relationships, Boyle's law, temperature volume relationship, that's Charles, mole volume, that's Avogadro, the ghost of Avogadro returns, the ideal gas laws, and the calculations. Also remember, Amnesty Weekend is this weekend. Friday, Saturday, and Sunday. Tutorial 1, Quiz 1 will come online. They will go offline midnight on Sunday. If you need to do any of the tutorials from one that you had not done before, or you have another shot at Quiz 1, do it. Any questions? All right. Kinetic molecular theory. Basically, it contends that all substances have an inherent attraction to each other. This is a lump of little buckyballs. They're magnets. The intermolecular forces of various forms. Well, this is a model for that. It's magnetism. And this represents basically a solid. In a solid, substances don't quite have enough energy to move away from each other. They just kind of sit in one spot and they vibrate. In a liquid, we put more energy into a substance. We can now slip and slide all over each other, but we still don't have enough kinetic energy to overcome molecular forces. In a gas, well, we do. In a gas, we have totally broken the attractive forces between substances. These guys are bouncing around madly. They bounce off each other, bounce off the walls, etc. We're talking about gases today. Note here the space between all the particles. Gas has a definite shape. It just takes on the shape of the container. All the space in between the particles allows gases to expand and compress, and they diffuse uniformly and rapidly throughout their container. Now, as they do this, you noted they were bouncing off the walls, right? Every time a gas particle bounces against something, it transfers a little bit of energy. This is a very interesting computer simulation. There are 500 little gas particles in this simulation. These walls are fixed, but the one up top floats. The thing that holds it up is the energy transfer from these little bits of gas that are here, bouncing against this movable barrier. And you can see it kind of goes up and down, but there's only 500 particles. Remember, a mole contains 6 times 10 to the 23rd particles. So, a whole lot of difference. This little bit of energy that's transferred every time something bounces is what gives rise to gas pressure. Atmospheric pressure is defined as the air molecules, the mixture, hitting various surfaces in the environment. Pressure from the atmosphere is about 15 pounds per square inch. Now that's actually a lot. You know, 1 square inch isn't much. Put 3 bags of flour on that 1 square inch, you're going to be squished a little bit, aren't you? There's a very interesting demonstration. This is a burner, the kind that you use to boil grease, put a turkey in, set the garage on fire, stuff like that. We're going to light this, take a 55-gallon drum with a little bit of water in it, heat it up, and seal it. So let's watch. That's the light part. There's our drum. You see it was smoking a little bit. Seal it up nice and tightly and plop it in a little kiddie swimming pool. After 30 seconds, that happens. Watch it again. It's really something. We used to be able to do this at UIC right there in the lecture hall. Yeah, it really does smash the little suckers shut. That's just from gas pressure. Really, it can amount to a lot. The only reason that we're not squished by the atmospheric pressure is that we have gas inside of us pushing back and a balance. Good thing. All right, measuring gas pressure. We use a barometer for that. Now, this room doesn't have a barometer, one of these old-fashioned kind. Our lab does, believe it or not. This is used to predict the weather. These are laboratory manometers. This one's recording. This guy, back in the old days, you would put it in line with a vacuum, and there's mercury in here. You would read the difference between the top and the bottom, and that would give you the gas pressure. This one's, today we don't use stuff like this. Today we use fancy electronic things in our vacuum lines. They can measure vacuum pressures very, very accurately and easily. In the lab on Wednesday, we are going to be using a pressure transducer, somewhat like this. This is my favorite. I grew up in Florida, and back in the old days in Florida, back in the old days everywhere, there were no such thing as satellites. And so there was no up-to-date weather forecast. You could not tell if a hurricane was coming. So you had one of these guys sitting on a shelf. Now this is sealed. It has air in it at, quote, atmospheric pressure. And as the outside atmospheric pressure changes a bit, the liquid will go up and down in the tube. However, if a giant storm is coming, this will not just go up in the tube, it'll squirt out the top, and you know it's time to get out of there. That's about all the warning we had to deal with these. Amazing. Laboratory manometers. This is a tube. What you do is you fill the tube with mercury. You have a big beaker of mercury down here. In the old days, we used to put our thumb over the top of the tube, stick our hand down in the beaker, let go. This would fall down until the vacuum offset the air pressure pushing down. Then you read the height from here up to where the bottom of this meniscus is. That height was atmospheric pressure. Typically, this is measured in millimeters of mercury. There are other units that are used. Atmosphere and millimeters are the ones we will use though. Millimeters are sometimes called torr. I'm not sure why. I never do. I just call them millimeters of mercury. And you can also measure, as we talked about, 15 pounds per square inch. We're never going to use that. So we just have atmospheres and millimeters of mercury. When we write 1 atmosphere, that is a definition. It's an exact number. Same thing with 760 millimeters of mercury. So this has doesn't have one significant figure. It's not used at all for significant figures. Neither is 760. 761 would, but not 760. Converting between atmospheres and millimeters is actually very, very simple. If you're given atmospheres and you need millimeters, all you do is multiply by 760. If you have millimeters and you want atmospheres, you just divide. Simply multiply and divide to convert the 2 units. Again, we will use both atmospheres and millimeters interchangeably. So, let's start off by talking about the pressure-volume relationship. This is referred to as Boyle's law. Again, the lab on Wednesday, we are doing Boyle's law. We'll talk a little bit about the lab at the end of the lecture. Basically, what Boyle said was the volume occupied by a fixed quantity of gas is inversely proportional to the applied pressure. Inversely proportional with regard to pressure simply means the more pressure you have, the smaller the volume. This is a little device that you can use to measure volumes and pressures, okay? It's a piston. Let's just look at this. If we take our piston and we put something very light on the top, we didn't even see our gauge wiggle, did we? Not at all. But if we put something substantial on it, like an animal, pressure goes up, volume goes down. Whenever you think of a pressure-volume relationship, just remember anvils. Pressure goes up, volume goes down. Any questions? Well, we can look at this without the anvil. What we're going to do here is mechanically compress this very slowly, monitor our pressure change, and we're going to plot it out. So let's get it started. Here it goes. Volume goes down, pressure goes up. We make a plot. As our volume decreases, the pressure increases. Now, this is nonlinear, isn't it? If you think about it, it has to be nonlinear because the gas that you're compressing has an inherent volume itself, doesn't it? If we compressed it all the way down, it would still have a volume. Therefore, this must be asymptotic to zero. This type of relationship is a hyperbola. Simple hyperbolic relationship. Pressure increases, volume decreases. Nobody in science really likes curved lines. We all like straight lines. They look better. Because this is hyperbolic, there's a very simple way to make them straight, and that is to do an inverse plot. So we plot volume versus 1 over pressure. When we do this, we get a beautiful straight line going through zero. Any questions? Well, mathematically, this represents Boyle's law. Boyle's law can be described as a volume directly proportional to 1 over P. The little proportionality sign looks like a Greek alpha, but it's actually proportionality. Can always be replaced in an equation by sticking in an equal sign and a constant. The constant is actually the slope of the line. We now have an equation that we can work with. Volume is equal to a constant times 1 over P. We can take this equation and rearrange it, but multiply both sides by P, we get PV equals a constant. So for our two situations with our piston, over here we have a pressure, we have a volume, and we have the constant. We'll call this P1, V1, and say it's equal to a constant. After we place our anvil on here, we have a high pressure and a small volume. But it's the same gas, isn't it? It's the same apparatus. So P1 or P2, V2 is going to also be equal to a constant. But because it's the same gas, the same system, the two constants must be identical. So that means that P1, V1 must equal P2, V2. This is the expression we use to describe Boyle's law. Initial state, final state, P1, V1, P2, V2. Any questions? Who was Robert Boyle? Well, he was kind of an arrogant-looking Englishman. I don't particularly like him. But this is Boyle's law nonetheless. Let's do a simple problem. We have 12.5 liters of gas. Our pressure is 0.82 atmospheres. We're going to adjust our piston. So the pressure is now 1.32 atmospheres. What's the final volume? Well, the equation we use is simply P1, V1, P2, V2. We're looking for final volume, that's V2. So we'll just solve it and pull out V2. There's V2. V2 is P1, V1 over P2. So we look at our problem. P1, That's the initial pressure. V1, the initial volume. V2, the final pressure. Substitute. Atmospheres will cancel. Simply multiply 0.82 times 12.5 divided by 1.32. Our volume would be 7.5 or 7.8 liters. That's not so bad, is it? Conceptually, it's simple once you know the basic equation. Let's do another. Here I put the volume in milliliters just because I could. And I did my pressure in milliliters of mercury, again, because they're equivalent. We have 150 mil sample of CO2, but it doesn't matter what the gas is. Avogadro told us that. And here's our pressure, 35 millimeters of mercury. The volume's decreased to 50 mils. Temperature held constant. We'll do that in just a minute. What's the final pressure going to be? We're looking for P2. V1, V1, P2, V2, and again we're solving for P2. P2 right here, going to be P1, V1 over V2. P1, 35 millimeters. V1, 150 mils. V2, 50 millimeters. Milliliters will both cancel. Our pressure is going to have units of 35 millimeters of mercury. Do the math. We get 106 millimeters of mercury. Now, what if I asked you to give me that in atmospheres? What would you do? Remember, millimeters of mercury in atmospheres are converted by the factor of 760. So we just simply take this, divide by 760, 0.14 atmospheres. Any questions? Well, there's a tutorial, and it is properly called Boyle's Law. Gas system has an initial pressure of 5 atmospheres. We have 5,050 milliliters of volume. We're changing our volume to 5.62 liters. What's the final pressure? All right, so we're looking for the final pressure in atmospheres. We have atmospheres in the problem. That's easy. This is milliliters, that's liters. They differ by 1,000, don't they? We can fix that. We take our 5.62 liters, multiply by 1,000, we get 5,600 mils. There's our initial pressure, initial volume, final volume, and we're after P2. Rearrange Boyle's law. P2 is P1 V1 over V2. Substitute, solve. What is this number? That's in atmospheres. The 3 significant figures. Let's set up and do one more. We have initial pressure of 2350 millimeters now. It's our volume. We're changing our pressure to 5.6 atmospheres. We're looking for a volume in liters. So we have to do 2 things. We have to get the initial and final pressures in the same units. and we have to change milliliters to liters. Milliliters to liters, simply divide by 1,000. We have 5 atmospheres. What is that in millimeters? Multiply by 760. And we're looking for V2. V2, P1, V1 over P2. We substitute, here's our answer in liters. We round it to 3 significant figures to get our answer. Any questions? Now, of all the tutorials that look like this that I wrote, this one has a bug in it somewhere that I've never, ever been able to figure out. Never been able to figure out. So sometimes you'll get something that's stupid. If you do, just click New Problem and get something different. But it's good practice. Any questions? All right, well, that was pressure volume. Let's look at temperature volume. This is a balloon. Okay? We are going to cool this balloon down to liquid nitrogen temperature, minus 196 centigrade. We will do that by gracefully dumping liquid nitrogen all over the balloon. Something like this. The balloon starts getting nervous, and here it comes. And as we cool the thing down, what happened to the volume? Well, it decreased. Now the liquid nitrogen is evaporating. As it does, temperature is increasing. As the temperature increases, the volume increases until we're back where we started. This is a simple, direct, linear relationship. Temperature goes down, volume goes down. Temperature goes up, volume goes up. But you know, science is a lot more than just playing with liquid nitrogen, although that is fun. This is an experiment that we can do. It's a little tedious to do. What we're going to do is take different molar amounts of the same gas, and we're going to put them in a little device where we can change the temperature and measure the volume. So we'll do this first with 0.25 volts. And sure enough, as we lower the temperature, the volume drops. That's what we expect. Nice linear relationship. But you never want to do an experiment like this with only one sample. So let's do it again with half a mole. And then again with 3/4 of a mole. Now we can say, yep, they're all nice and linear. But if you look at these lines, they all look like they're going somewhere, don't they? If you take and extrapolate these lines down here to 0, by George, they all intercept at the same spot. That spot is minus 273.15 centigrade. We never call it that. This temperature right here, minus 273, is what we refer to as absolute zero. At absolute zero, the volume of the gas drops to 0. Now we know it never can. That's why you have to extrapolate. We also define a new temperature scale based on this point. We call that the Kelvin scale. K is the unit, and we're going to let this be zero. Absolute zero is 0 on the Kelvin scale. Whenever you do calculations involving the gas laws, you must use the Kelvin scale. All right, we'll return to that in a second. We have shown that volume was directly proportional to temperature. Remember, we can take our proportionality and make it an equal K out of it. So V is equal to KT. Let's do what we did last time and isolate our K. K is simply V divided by T. Now with our balloon, we can easily see we had two states. Here we had very low temperature, V1 over T1 is equal to a constant. We allowed this to warm up. V2 over T2 is still a constant. Just like the PV relationship, these two are the same constants, same balloon, the same gas. Therefore, V1 over T1 equals V2 over T2. This is what we call Charles's law. Any questions? Well, how about who was Charles? That was Charles. Kind of a nice looking guy. Ruddy, whatever, Frenchman. Anybody know who this is? Barry Manilow? Dead ringer for Charles. Nonetheless, first time I saw that, I couldn't quite believe it. But anyway, this is Charles. Charles was a very interesting person. He was a balloonist. In fact, he was the very first person to actually fill and ride a balloon. Something like this. Oh, there we go. No, this is his balloon. His balloon was big. It was filled with hydrogen gas. Made the hydrogen gas by reacting sulfuric acid with iron. You get iron 2 sulfate and hydrogen. This reaction also gets really, really hot. So as the hydrogen comes out of this little generator here, it's really hot hydrogen, really hot. Fills the balloon. As it expands up into the balloon, it cools. And the balloon would kind of collapse on itself. And then as you pump more in, it would go up and down and up and down. And I think that's actually where he got the idea for his law. Watching his balloon with the hot hydrogen. So, he filled this thing. Went for a little ride across the French countryside. Went up about 1,000 feet, a couple bottles of wine in the gondola with him, and we're just having a great time sailing over France. After a while, he said, gee, I think it's time to come down. He looked and he saw this little village. And said, that's a good place to land. But French peasants at the time that occupied this village did not often see people flying overhead in balloons and coming in for a landing on their territory. And they did as you might expect a French peasant group to do. As it came down, they attacked it with pitchforks, knives, dogs, rocks. Fortunately, they didn't do the flaming torches. Right? We've seen that. Charles lived through it, but he never took another trip down that way. Never did. Nonetheless, hydrogen gas did have a future in terms of ballooning. Just before the Second World War, it became very fashionable to build large airships. This is a dirigible. It was German, Nazi thing, called the Hindenburg. It was huge, absolutely huge. It was designed to hold about 50 people, and it was designed to fly from Berlin all the way across the Atlantic to New Jersey. They flew it around Europe for a little bit, make sure it worked. Then they took and they flew it across the Atlantic all the way to New Jersey. Got there with no problem. However, in New Jersey, there was a thunderstorm. The skin on this was aluminum, thin aluminum. It developed an electrical charge. So as you're in your balloon and you're coming down, how do you do that? You release hydrogen gas, which is extremely flammable. So you have a charged balloon and hydrogen gas coming out, and as it came in for a landing, it exploded. It was a terrible disaster at the time, and they didn't use hydrogen anymore. That's why we went to a helium economy, but we're actually almost out of helium now. So, whatever. Any questions? As I said, Kelvin. Kelvin must be used in all gas law problems. Now we know that water freezes at 0 centigrade and boils at 100. Remember that Kelvin is 273 degrees more. Therefore, Kelvin, or freezing point of water, is 273. Boiling point is 373. The convenient part is there's 100 little degrees here, right? There's 100 little degrees here too. So, the two are easily convertible. They differ by the factor again of 273.15, which we typically just round to 273. Let's just do a couple, make sure. Oh, they always differ by 273. Important things to remember. And Kelvin is always bigger. Okay? Kelvin is bigger by 273. So if I give you a little list, and I say, what are these in Kelvin? Remember, Kelvin is bigger by 273. So it's simple. 1,000 plus 273 is 1,273. Minus 150. So you have to do the negative thing here. But it winds up 123. 100 degrees we just saw, 373 Kelvin. Any questions? Well, let's do a Charles problem. We have a 50 mil sample. We're at 26 degrees centigrade. We heat it at constant pressure until its volume is 62. What's the final temperature? So, we know Charles's law. In the problem, we're given V1, T1, and V2, and we simply need to solve for T1. That should be T2. I always forget to change that. We're solving for T2. Here's Charles's law. T2 is what we want. V2, T1 over V1. V2, 64 mils. V1, 50 mils. T1, well, this is given in centigrade, isn't it? We must use Kelvin. So we'll take this one and convert it to Kelvin. If you add 273, you get about 300 Kelvin. All right, so set up your problem, do your substitution. V2, T1, V1. Milliliters cancel. 62 times 300 divided by 50. We're at 373 Kelvin. 374-ish. Now once again, if I asked you for that in terms of centigrade, what would you give me? Remember, Kelvin is always bigger by 273. So this minus 273 is 101. Question. All right, well, if Boyle has a tutorial, Charles has to have one too. That's only fair. Gas system has an initial volume and temperature of this and that. If the volume changes to that, what's the resulting temperature? Our temp is given in centigrade. We must convert that to Kelvin. This is milliliters, that's liters. We have to do that conversion as well. Looks something like this. 106 plus 273 is 379. Here's our liters. Multiply by 1,000 to get milliliters. We are looking for T2. T2 is V2 T1 over V1. Here's my substitution. Do the calculation. And we're 264. Any questions? Well, you know, we saw this experiment a little bit earlier. We have different mole quantities of gas, change the temperature, measure the volume. Setting up and doing an experiment like this is a bother. Not real difficult, but it's just a real bother. So you want to try to get as much as you can out of the data that you've collected. So we could ask the question, if we hold the temperature constant and just change the number of moles, what's our relationship? Looks like it's going to be linear, doesn't it, by George? Linear and direct. Makes sense because the more gas you have, the bigger your volume, right? Right. This is the mole-volume relationship. Basically, number of moles versus volume, nice linear thing. This is Avogadro's law. It goes to Avogadro, remains. The relationship between number of moles is linear. Again, this is Avogadro. Okay. Boyle's law, we said volume was proportional to 1 over P. Charles's law, we said volume was proportional to T. Avogadro's law, volume is proportional to N. Well, if volume is proportional to all three of these guys, you can simply combine this into a single equation. We can say that volume is proportional to NT over P. Now, every time we've had proportionality sign, what do? We get rid of it. Put in a KT. But you know what? I'm tired of using K. I'm going to put in a different letter because I can. And what I'm going to put in is an uppercase R. And I'm going to give it a name. I'm going to call it the universal gas constant. The symbol is R. So just like this, except R instead of K. Okay, we can do that. That's all legal. And we have an equation that we can call the ideal gas law. Volume is equal to some constant times NT over P. Well, that's a fine equation, I suppose. But if you take and rearrange this a little bit, it becomes a fun equation. Let's multiply both sides by P, and we get PV equals nRT. Kind of rhymes with itself. PV equals nRT. This is what you write for the ideal gas law. PV equals nRT. Well, the problem here is, what's R numerically? If we knew what R was, and we knew these guys, we could calculate any missing quantity, couldn't we? Well, we have to know what R is. Turns out, we can calculate that. Because Avogadro told us that 1 mole, that's N, at 273 Kelvin, that's T, 1 atmosphere, that's P, has a volume of 22.4 liters. That's V. We know everything here except R. R is PV over NT. So, let's just see what it is. 1 atmosphere, 22.4 liters, 1 mole, 273 Kelvin. First thing you should notice is that nothing cancels, does it? Second thing you notice is when you do the calculation, you get this strange number, 0.082057, with units of liter atmosphere per mole per Kelvin. Nonetheless, this is R. Now, quite honestly, I can't remember this number either. That's fine. Anytime you need it on an exam or a quiz or whatever, it will be there. Okay? Also, whenever you do these problems, the units must match. Your pressure must be atmospheres, your volume must be in liters, temperature in Kelvin. So let's do a problem. We have argon, although it doesn't matter what the gas is. We're looking for how many moles. Well, that's N. We have 18.6 liters, 293 Kelvin. Our pressure is 2.3 atmospheres. We will simply use PV equals nRT. Looking for moles, that's N. It is PV over RT. Our pressure, 2.3 atmospheres. Our volume, 18.6 liters. R, this guy, 0.08 2, 1. Units of liter atmosphere per mole per Kelvin. And finally, our temperature, 293 Kelvin. Atmospheres will cancel. Liters will cancel. Kelvin and per Kelvin cancel. And here we have per mole in the denominator. It comes up top. We get 1.8 moles of gas. Again, respect the units. Liters, atmosphere, Kelvin. Our third tutorial is simply called Ideal Gas Laws. I believe on your site it's called PV equals nRT. PV, maybe no equal. PV nRT, something like that. So that's what it is. Here we have a gas system. Volume, moles, and temperature. There's our volume, 0.396 moles, our temperature in Kelvin. What's the pressure? In atmospheres. Our volume, number of moles, and temperature are all in the correct units. We're going to use the ideal gas law, that's PV equals nRT. Solve for P, nRT over V. Substitute, and simply do the calculation. What if I had asked for this in millimeters? Because it does that sometimes. You would simply take atmospheres, multiply by 760, and get 1,400 millimeters. Questions? Go ahead and look at one more. Here we have atmospheres, here we have milliliters and moles. We're looking for the temperature in Kelvin. Only thing we have to fix here is remember milliliters must be liters. So we divide that by 1,000. 8,000 divided by 1,000, 8.35. Number of moles, there's our pressure, what's the temperature? Simply rearrange, plug it into PV equals nRT. T is PV over nR, PV, nR. Do the calculation. We're at 225 Kelvin. If we wanted centigrade, what would we do? Subtract 273. Any questions? All right, well, let's look at some exam questions then. This was our last tutorial. I put this on an exam, I've said this to you many times, as a stupid question. So everybody would get one right and they'd feel good about themselves. Under conditions of fixed temperature and amount of gas, boil law requires what? P1, V1, P2, V2. That's the boiled law we all know and love. How did we get this? Because we said that PV was equal to K, a constant. So that's true. And finally, what is this? If we take both sides multiplied by P2, we get P1 or P2 up here. Again, multiplied by V1, you get V1 there. This is the same as Boyle's law. So all of these are correct. So I put this on an exam, and again, huge number of people missed it. I felt miserable. So I did it again with Charles. Which of these is Charles's law? Well, T1, V1, T2, V2, that sounds a whole lot like Boyle, doesn't it? TV is a constant? No. T over V was a constant. This is our Boyle's, or Charles's law. Remember, V over T was a constant. So this guy is clearly wrong. TV is not a constant. V over T is a constant. If you take and rearrange this, what do you get? Well, you don't get this. That's wrong too. This one was a none of the above. Again, everybody missed it. Oh well. Okay, calculation problem. 450 mils of gas at 1 atmosphere. We reduce the pressure to 5 atmospheres. So what is our resulting volume? This is a Boyle's law problem, isn't it? P1, V1, P2, V2. P1, V1, P2, and we're looking for our volume in milliliters and or liters. V2 is going to be 450 times 1 divided by 5, and that's 90 grams. When you do something like Boyle's or Charles, you don't always have to use liters, but PV equals nRT, you must. When comparing temperature readings on Celsius, that's centigrade, and Kelvin scales, which is true? 1 Kelvin is a larger temperature change. Nope, they're the same. 1 Kelvin, centigrade and Kelvin are never numerically equal. Well, of course they're not. You take Kelvin and you subtract 273 to get centigrade. That's right. Only readings on these centigrade scales can be converted to Fahrenheit. Oh, that's stupid. Any questions? All right. Things to know about the KMT. Gases consist of molecules in constant and random motion. Pressure arises from collisions. No attractive repulsive or repulsive forces exist. That's not true, actually. At very high pressures, you do get attraction. And finally, the volume of the molecule is negligible. Yeah, pretty much. Now, the whole chapter here in 3 little videos.
If the number of gas molecules in a container is doubled with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
Number of moles and pressure are directly proportional.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore, so does gas pressure.
Pressure and temperature directly proportional.
If the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
If volume goes down, pressure goes up. Inverse. Any questions? Now, I said that on Wednesday we are going to do lab number 10. That's our last lab. That's sad in some ways. We will continue to have the last couple of classes over there, but nonetheless, it's our last lab. And the last lab is pressure volume over the Boyle relationship. For these, we're going to use these LabQuest little mini computers. We'll take and we'll plug a syringe and a gas pressure sensor into the thing. Basically, what you're going to do is adjust, once you get it all set up and the program running, you will adjust the plunger here. As you do, you will get a pressure reading. This probably works best if you work together, because you need somebody to hold the syringe very steady while somebody writes down all the numbers. So work together. So when you do this, these devices are a little complicated to use. The handout that's on Blackboard is a new one, and it describes how to do the experiment, which buttons to push, which ones not to push. Because if you push the wrong button, you have to start over. Don't want to do that. Basically what you do is you will collect data. You will then use their graphing routine. You will graph that data. It will be nonlinear. We know that. Hyperbolic relationship. You will do an analysis of the graph, and it will tell you exactly how close your points fit a hyperbola. You will then take your data set and you will do a reciprocal plot, 1 over volume versus pressure. It should be nice and linear. You will do a correlation coefficient now under Analyze, and that will tell you how closely these things fit a straight line. On the sheet that you hand in, you will put all of the pressures down and the volumes, the correlation coefficient for the curve plot and for the linear plot. Any questions? Please take a look at the handout, because again, it's a little complicated to use the device. And you can screw it up and have to start over. Here's our tutorial, 3 more today. We have 1 tutorial left. That's in chapter 11, radioactive decay. Remember, 5 points each. And one more time, just in case you came in late, Amnesty Weekend, Friday, Saturday, and Sunday. That's this weekend. Tutorials 1, quiz 1 will be online. Do them, get extra points if you need. They go offline on midnight on Sunday. Any questions? All right, guys, I will see you Wednesday.